Hi there. Today we're going to start looking at the parts of a graph. And you did some of this in Algebra 2, but we're going to get into greater detail. So I've got a list here. There are quite a few things that we could say about a graph. See, I got a whole long list here. But we're going to hit the main things. All right. So first of all, what are we talking about when we talk about domain and range? Domain and range. Well, one of my teachers used to say all the time to me, domain of X, range of Y. Domain of X, range of Y. Domain of X, range of Y. So domain, we're talking about X. Where is X? Range, we're talking about Y. Where is Y? And in particular, what we're going to be getting into in pre-cal is graphs that have gaps in them. So for instance, we might have a graph like this right here, where maybe we have a piece shooting down like that, and a piece coming across like that, and there's a gap right here in between. And there's a gap right, oh, I didn't draw that very well, but I can draw it better. And there's a gap right there in between. Now these gaps, well, that's a piece of vocabulary you should know as well, but I'll come back to that. What's important right now here is there's a gap right here. So let's suppose that this vertical line right here is x equals 3. And suppose that this horizontal line right here is y equals 2. Then when I'm describing the domain, x, I would say that this graph goes all the way to the left. If I follow it, x is left, right. If I go all the way to the left, it goes to negative infinity. If I go all to the right, it goes to positive infinity. So I could say that x is all real numbers, except, wait a minute, it jumps over right here. It never hits x equals 3. And so the way we say that is x is all real numbers except 3. X is all real numbers except the number 3 because x jumps over. We can follow this graph to negative infinity. We can follow it up to 3, but we can't quite reach 3. But if we jump over 3 and keep going, we can go all the way over to infinity. Now similarly, I can do that with y. I can say, well, this graph goes down to negative infinity and up to positive infinity. So that's all real numbers, except it skips over 2. So all real numbers except 2. So domain and range, not always all real numbers. There can be gaps. Could there be multiple gaps? Yes, graphs could have multiple gaps. And we'll study some of those a little bit later in the course. What else could we do with domain and range? Well, we might want to talk about graphs that stop. For instance, suppose I did the graph of y equals the square root of x minus plus 4, x plus 4. Well, go to your graphing calculator. You'll find that the graph looks like this. And the y-intercept right here is at negative 4. Excuse me, the x-intercept is at negative 4. So what if I wanted to describe the domain here? Well, how far to the left does the graph go? It goes to negative 4. So I would say x goes to negative 4. How far to the right does it go? It goes forever, so to infinity. Now, then we have the brackets and parentheses, and I know some of you are still struggling with that. Bracket means it's included, and parentheses means not included. So I ask, does x actually reach negative 4? Well, it does. I have a colored in dot there. And you can trace on your calculator. Hit trace, type x equals negative 4, hit enter. You'll see there's a point there. There's the point negative 4, 0. So negative 4 is included. What about infinity? Well, the graph is heading toward infinity, but infinity is more of an idea than a number. We can never really get there. And so we say infinity is not included. What about range? Well, range again is y, which is up, down. So we ask, how far down does this graph go? Well, the lowest this graph goes is 0. So we would say 0. And since 0 is included, that dot is colored in, included. And then what about how high does the graph go? Well, as I follow this graph, it's heading off to the right, but it's also heading upward, and it's going to keep heading upward forever, so to infinity. So there's the range of that graph. Now what if a graph has a barrier like the one I drew a little while ago, where the graph approaches the barrier but does not touch it? So for instance, the line x equals 3, as I'm showing right here, or the line y equals 2, right there. Well, those are called asymptotes, and that is spelled A-S-Y-M-P-T-O-T-E, asymptote. So if you were asked to list the asymptotes of this graph, you would say it has an asymptote at x equals 3 and an asymptote at y equals 2. Now, in addition to asymptotes, some graphs have a hole in them. You might have seen these last semester, or excuse me, last year when you were taking Algebra II. Sometimes a graph will have just a little tiny hole in it, like that right there. Those are usually called holes. There's another term for them, and I'm going to talk about that other term in just a minute. Now, another thing that can happen, particularly when you're doing piecewise defined functions, is a graph can have a jump in it. You could have the graph chugging along, just minding its own business, and then all of a sudden it gets a hiccup, and it jumps over to a new location. That's called a jump. Well, when any of these three things happen, whether you have an asymptote, or you have a jump, or you have a hole, these are called discontinuities. All of these together, whether it's a jump, or an asymptote, or a hole, is called a type of a discontinuity. D-I-S-C-O-N-T-U-N-I-T-Y. And when you start talking about discontinuity, discontinuity means jump or break in the graph. What if a graph has no jumps or breaks? What if you can trace a graph forever and it never has any gaps, never has any asymptotes, no jumps, no holes? We would call that a continuous graph. Now, what about for these? Well, each one of them kind of comes with its own vocabulary. I'm sorry about that. But here's the good news. The jump one is called jump discontinuous. So jump discontinuous. And I'm just going to write D-I-S-C-O-N, short for discontinuous. What about when you have an asymptote? Well, if you follow an asymptote up, 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 it's heading toward infinity. Or if you follow this asymptote down, 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 heading toward negative infinity. Follow this asymptote to the right, dot, 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 to the right, heading toward infinity. Follow this asymptote toward the left, dot, 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 heading toward negative infinity. So these are called infinite discontinuities. Infinite discontinuities because the asymptotes are heading toward infinity. Now, what about a hole? Well, there are two names for a hole. One name is, it can be called a point discontinuity because it's only missing a point. In that case, you would say where the point is. So, for instance, suppose this hole is the point 1, 4. You would say this graph has a point discontinuity at 1, 4. The other name for these is removable discontinuity. Now that's a weird name because it seems like something's already been removed. What do they mean, removable discontinuity? Do they mean we can take away the hole? Well, they do. We can take away the hole. And I'm not ready to talk about that yet, and you're not ready to listen to that yet. But in calculus, you're going to find that we can remove the holes. So removable discontinuity. What else do you need to know in order to describe a graph? We know domain and range. We know asymptotes. We know jumps. We know holes. We know holes as point discontinuities or removable discontinuities. We know asymptotes as infinite discontinuities. We know graphs with no breaks in them are called continuous. Well, the other things you're going to want to know have to do with where a graph peaks and where the graph falls. So let's suppose you had a graph like this parabola right here. And so here's a parabola, x-axis, y-axis, heading down forever, heading down forever. And let's suppose that the vertex right here is at the point 3, 8. Okay? Well, that 0.38 right there is called an extreme. And there are two kinds of extremes. There are extremes like this that are the peak of a hill. There are also extremes like this, which are the bottom of a valley. And let's suppose this one is located at -2, -4. These are two kinds of extrema, the extremes. Peak of a hill, bottom of a valley. Now, when you're at the peak of a hill, that extreme, because it's at the very tippy top, we call it a maximum. And you can bet, since this one's at the very bottom of a valley, we're going to call it a minimum. Now, one other thing closely related to these peaks is local peaks or valleys and absolute peaks or valleys. If you hit a peak and it is the highest the graph ever hits anywhere, we call it an absolute maximum. So this isn't just an extreme, it isn't just a maximum, it is an absolute maximum. This isn't just a minimum, since it's the bottom of a parabola. Parabolas only have one bottom. This isn't just any old minimum, it is the absolute minimum. As in, the graph absolutely never goes lower than that. Well, what's the opposite of that? Well, the opposite of that is called a local maximum or minimum. And you see those when you get to higher degree functions like third power, fourth power, fifth power, and so on. For instance, suppose you had an S-shaped curve like this. So let's suppose that we have this point right here is -2, 5. And suppose we have this point right here, which is 6, -1. All right. Then I would say that this is a maximum, because it is the peak of a hill. But is it the highest the graph ever goes? Well, no, because right over here the graph goes even higher. So this is not an absolute maximum. We call this a local maximum. And what about minimum? Well, over here we have a minimum. That's the bottom of a valley. But is it the lowest the graph ever goes? Well, no, because over here the graph goes even lower. So we would call this a local minimum. It's the lowest point among its neighbors, but it's not the lowest point anywhere. This is the highest point among its immediate neighbors, but it's not the highest point of the entire graph. Now, while we're looking at this picture, there's one last thing I want to show you guys, which is called an increasing and decreasing interval. Now, this has to do with slope. And remember, slope is positive if the graph is going like this, up and to the right or down and to the left. Negative if the graph is going like this, up and to the left or down and to the right. And if you look at this graph, you can see that in some sections it's got a positive slope, and in some sections it's got a negative slope. Let me get this out of the way right here. If we look at this section right here, you can see that that section has a positive slope. And similarly, if you look over here, you can see that this section has a positive slope. And then this section in the middle has a negative slope. What about right at the maximum? Right at the maximum, the slope is not positive nor is it negative. It's flat just for a moment. So the slope there is 0. And similarly, right here at the minimum, the slope is 0. I'll show you. Suppose I put my ruler up against my curve. Well, if my ruler is touching the curve like that, you can see how the ruler has a positive slope. And as I'm touching like that, again, you can see positive slope. And as I'm touching like that, again, you can see positive slope. But as I come over here and I crest the hill, right there, you can see It's perfectly flat, the slope is 0. And then as I keep following along the hill, you see how the slope gets negative, 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 negative. Oh, but right there you can see how it goes flat again. See how the slope there is 0, and then the slope starts rising again. So in this region we have a positive slope, that's called an increasing interval. In here we have a negative slope, that's called a decreasing interval. And in here we have a positive slope again, a increasing interval. So somebody asked me, where does this graph have an increasing interval? I would say that this graph is increasing. Okay, now this part's going to trip you up a little bit. When we describe increasing and decreasing intervals, we don't describe them in terms of y, we describe them in terms of x. That's because calculus, everything is based on x. Everything's based on functions. Functions are dependent on x. X is the independent variable. So we're going to describe things in terms of x. So let's look at this increasing section over here. If I look at the x's, well, this graph is going down, but it's also going to the left. How far to the left? Negative infinity. And what about to the right? As I go this way, I'm going up, but I'm also going to the right. How far to the right? Negative 2. So I would say that this graph is increasing when x goes from negative infinity up to negative 2. And I also have increasing slope on this section. So again, we're looking at x, left, right, not up, down. How far to the left do we see a positive slope? Well, right here at 6. So x starting from 6. And then we follow this graph. We're going to the right. We're going up, but we're also going to the right. How far are we going to go to the right? Forever. So 6 to infinity. What if somebody asked me what the decreasing interval was? Well, that's this piece right here in the middle. That's where the slope is negative. Decreasing. Again, we're going to describe in terms of x, not y. So you might be tempted to say the graph goes from negative 1 to 5 because that's y. But we're not looking at y, we're looking at x. How far to the left do we see a negative slope? Negative 2. How far to the right do we see a negative slope? Positive 6. So their decreasing interval is from negative 2 to positive 6. And you'll notice I'm using parentheses, not brackets, because the slope is not negative here. The slope is 0 here. The slope is not negative there, nor is it positive. It is 0 there. So that's why I did not include them. So, a lot of stuff to add to your vocabulary. You knew about domain and range. We talked about it a little bit more. We talked about domain and range for missing points. We talked about increasing intervals, decreasing intervals. We talked about continuity and discontinuity, the 3 types of discontinuity. And we looked at maximum and minimum, whether they be local or absolute. And you know